Imagine typing a few words and getting back this incredibly realistic image. I mean, just a few years back, that was pure science fiction, right?
Absolutely. It felt impossible.
But now, generative AI images are really transforming creative fields. People are making just breathtaking art, seemingly from nothing.
Mm-hmm.
So today, we're doing a deep dive into the tech behind all this magic diffusion model.
Yeah, the core engine driving a lot of this.
Our mission. We want to unpack how they actually work, look at the tools you'd use, like the Hugging Face diffusers library everyone talks about, and then get into the real craft of fine-tuning them.
Making them do exactly what you want.
Exactly. And then crucially, how do you optimize these things and actually deploy them, for real-world use?
Right, taking it from a cool experiment to a usable tool.
We're drawing on insights from mastering diffusion models, from training to deployment, and the developer's masterclass. Fine-tuning in production with diffusers.
Both excellent resources.
Okay, let's get into it. How do these models go from just random noise to, well, art? And then the big question, how do you make them create what you have in mind?
It's a fascinating process, actually. There's a surprising sort of elegance to it when you break it down.
Okay, so let's start right at the beginning then. To really get it, we need to understand the foundations. What exactly are diffusion models? And I heard something about thermodynamics. That sounds fundamental.
It does, doesn't it? And it is. Diffusion models are, well, they're cutting-edge generative AI algorithms. They're particularly good with images, as you said. And yeah, the core idea is inspired by non-equilibrium thermodynamics.
Okay.
Think about how things naturally go from order to disorder, like ink spreading in water. Diffusion models kind of learn how to reverse that process, at least mathematically. How to go from pure disorder noise back to an ordered, coherent image.
Wow, okay. Reversing entropy, almost.
Sort of, in a computational sense.
Yep.
It happens in two main stages. First, there's the forward diffusion process.
Right.
Imagine you take a clean image and you just start adding a tiny bit of Gaussian noise, then a bit more, and more over lots and lots of steps.
Okay.
Until eventually, all you have left is pure noise, just static. The crucial thing here is this part involves zero learning. It's a fixed process, like a predetermined recipe for adding noise. It's a Markov chain, meaning each step just depends on the last one, following a set noise schedule.
So step one is just systematically messing up the image. The AI isn't learning anything yet. Got it.
Exactly, no learning there. But then comes the reverse diffusion process. This is where the magic, the learning happens.
Wow, yeah.
A neural network, usually a specific type called a UNet, is trained to basically undo the forward process. It learns to predict the noise that was added at each step and then subtracts it out iteratively.
Iteratively. So step by step.
Step by painstaking step, yeah. It gradually turns that pure noise back into something that looks like the original data distribution, like a coherent image.
So the UNet is the brain doing the cleanup job, figuring out the noise to remove. And you mentioned its structure is important.
Precisely. The UNet is the absolute workhorse. Its architecture is really well suited for this. It has an encoder-decoder structure. Think of it like compressing the noisy image down to its essence and then expanding it back out.
Okay.
But the key things are these skip connections. They're like little data highways that bypass the compression-expansion bottleneck. They connect layers from the encoder directly to corresponding layers in the decoder.
Why is that important?
It means fine-grained details from the earlier, noisier stages aren't lost during the process. They get carried across, helping the UNet reconstruct sharp details as it denoises. So the UNet takes the noisy image and the current time step as input, and its job is to predict the noise for that specific step.
And what about these schedulers you mentioned?
Right, the schedulers and noise schedules, they're kind of like the conductors of this whole orchestra. They implement that noise schedule we talked about and dictate the sequence of time steps for the reverse process, the denoising.
So they control the tempo.
Exactly. How fast or how gradually the noise is removed. And different schedulers, like DDPM or DDIM or popular ones, they offer different trade-offs. Some are faster, but maybe slightly less detailed. Others are slower, but potentially higher quality. They're interchangeable, which is neat.
Interesting. And you said it visually looks like starting with a rough outline.
Yeah, it's quite fascinating to watch. The generation often starts by committing to a very coarse, blurry outline, and then over the denoising steps, it progressively fills in the finer and finer details, almost like how a painter might work.
Okay, that gives a much clearer picture of the theory. But theory is one thing. How do you actually use these? What are the practical tools?
Right. Once you've got the how it works part down. You need the right tools to actually build something. And for diffusion models, the Hugging Face Diffusers library has really become the go-to choice for a lot of people.
Why is that? What makes it stand out?
It boils down to some core design philosophies they have, which really impact how you work with it. First, they prioritize usability over performance, at least by default. Meaning, when you load a model, it comes in high precision, minimal funny business or optimization. It's designed to just work out of the box. Performance tuning is something you can choose to add later.
Okay, that sounds beginner-friendly.
It is, but the second point is interesting. Simple over hazy. They don't try to hide all the complexity. Things like managing which device your model runs on, or the fact that the scheduler and the UNet are separate things, they expose that.
Why would they do that? Isn't easy better?
Well, easy often means hiding things in abstractions, which can be great until something goes wrong or until you want to experiment. Simple here means the components are understandable and you have explicit control. It makes debugging easier and opens the door for more advanced tinkering.
I see. More control, less magic black box.
Exactly. And that ties into the third point, tweakable, contributor-friendly over abstraction. They often use what they call a single file policy for models or components. Sometimes they even prefer copy-pasting code rather than creating super complex abstractions, just to avoid repeating a few lines.
That sounds counterintuitive to standard software engineering.
Right.
DRY principle and all that.
It does. But their reasoning is it massively lowers the barrier for people to understand a specific part, modify it for their own needs, or even contribute back improvements without needing to understand the entire intricate system or risking breaking unrelated things. It's very practical for a rapidly evolving field like this.
So it's like they give you a set of Lego bricks, not a pre-built model car. You see all the pieces.
That's a perfect analogy. And the library is literally built around these core bricks. You have pipelines like Diffusion pipeline. These are the high-level, easy-to-use wrappers for common tasks like text-to-image. Think Stable Diffusion pipeline.
Okay, the user-friendly entry point.
Then you have the models themselves, like the UNet, the VAE, which decodes the image, the text encoder. Crucially, these are treated as independent Python classes, inheriting from model mixin. They're separate bricks.
Got it.
And finally, the schedulers, inheriting from scheduler mixin. These are the algorithms for the denoising steps we talked about, like DDIM or PNDM, and they're designed to be easily swappable.
Right, so this modularity, treating the UNet and text encoder and scheduler as separate things you can plug and play. What's the big advantage there in practice?
This is where it gets really powerful. This modularity is precisely what enables advanced fine-tuning techniques. Think about LoRA low-rank adaptation, which is super popular. LoRA works by injecting small, new trainable weights only into specific parts of the model, usually the attention layers of the UNet. The rest of the massive model, billions of parameters, stays frozen. You can only do that kind of surgical modification easily if the UNet is an accessible separate component. If it was all one big black box, trying to inject weights into specific layers would be a nightmare, if not impossible. So this design choice directly enables customizing these huge models efficiently.
Okay, that makes total sense. Modularity equals flexibility for customization. So let's talk about that customization. You've got the theory, you've got the diffusers toolbox. How do you actually make a general model like Stable Diffusion create images in your specific style or generate pictures of your specific product or even your cat?
Right. This is the domain of fine-tuning. Essentially, you take a powerful pre-trained model that already knows a lot about the world, and you adapt it using your own smaller data set that represents the specific thing you care about. You update its weights just enough to learn your new concept or style.
And how do you approach that? Is it just one method?
Broadly, there are two main strategies. The traditional way is full model fine-tuning. Here, you're actually updating all or at least a very large portion of the model's parameters.
Sounds intensive.
It is. It can give you extremely high quality, really bake your style or subject into the model. But it's computationally very expensive. You need a lot of GPU memory. We're talking significant VRAM, often more than 12 gigabytes, maybe much more. And the resulting fine-tuned model files are huge, several gigabytes typically.
Okay, so a powerful but resource-hungry, what's the alternative?
The alternative, which has really taken off and made custom AI accessible, is parameter-efficient fine-tuning, or PEFT.
PEFT. heard a lot about that.
Yeah, the core idea of PEFT is you freeze most of the original pre-trained model's weights. Billions of parameters just stay locked, and you only train a very small number of new or specific existing parameters.
So you're adding just a little bit of extra learning.
Exactly, or you're cleverly adapting existing pathways. This dramatically cuts down the memory needed, the computation time, and crucially, the final file size of your customization. We're talking megabytes instead of gigabytes in many cases. It makes fine-tuning feasible for people without, giant GPU clusters.
That's not just a technical tweak. That sounds like a genuine game changer.
Yeah.
It democratizes things, right? Before PEFT, maybe only research labs could afford to customize these models.
Pretty much, yeah. Or large companies. Now, someone with a decent consumer GPU can actually sculpt these models towards their unique style or need. It's huge.
So within PFT, what are the main methods people should know? You mentioned LoRA. Are there others? What are the trade-offs?
Yeah, there are a few key PFT methods, each with its niche. Let's start with DreamBooth. DreamBooth is really specialized in teaching a model a new subject, like your specific cat or a particular branded object. It aims for really high fidelity on that subject.
How does it do that?
It uses a unique identifier token in the text prompt, like
Yeah.
a photo of a Skex cat, where 6 is your unique token. And it often uses something called prior preservation loss. That's basically a technique to show the model generic pictures of cats alongside your specific cat pictures. So it learns your cat without completely forgetting what other cats look like. It prevents overfitting too badly.
Makes sense. Keep the general knowledge while learning the specific. Is it efficient?
It's efficient compared to full fine-tuning, but it's still one of the more resource-intensive PEFT methods. You'll likely still need over 12 GB of VRAM, and the output files can be fairly large for PEFT, maybe 2 to 8 gigabytes sometimes, depending on how it's saved. But the quality for injecting a specific subject is often considered top-notch.
Okay, so DreamBooth for high-fidelity subjects. What else?
Then there's textual inversion. This is the most lightweight method. It doesn't touch the main model weights at all. Instead, it trains only a new placeholder word, a special token, in the vocabulary of the text encoder part of the model.
Just learns a new word.
Essentially, yes. It learns a specific vector representation for your concept associated with that word. The resulting files are incredibly tiny, like maybe 100 kilobytes. Super portable.
Wow. But what's the catch?
The catch is limited expressive power. Because you're only tweaking the text input, it's usually best for simpler concepts, or maybe capturing a specific face. It might struggle with complex styles or highly detailed objects compared to other methods.
Okay, tiny files, easy to share, but maybe less powerful. What's the third one?
The third, and probably the most popular right now due to its balance, is LoRA, low-rank adaptation.
Right, you mentioned this one earlier.
Yeah, so LoRA, again, freezes the original model weights, but it injects these small trainable matrices called low-rank matrices into specific parts of the model, typically the attention layers within the UNet.
What do these matrices do?
Think of the original huge weight matrices in the UNet, like a massive, complex control panel with millions of knobs. Training all those knobs is expensive. LoRA adds a much smaller, simpler set of master control knobs, the low-rank matrices that can effectively influence the big panel's output without touching the original knobs. You only train these few master knobs.
Okay, that's a helpful analogy. Efficient control.
Exactly. It learns the change or the adaptation needed for your style or concept in these small matrices. This gives a really excellent balance between quality and efficiency. The output files are much smaller than DreamBooth, typically 2 to maybe 200 megabytes. And the VRAM requirements are more manageable, often doable with 8 GB or more, depending on the setup.
And what's LoRA best for?
It's fantastic for learning new artistic styles, character designs, or even general concepts that aren't necessarily tied to one specific object like DreamBooth. It's become the real sweet spot for many users.
That's a brilliant breakdown. So let me see if I have this right. If I just want the model to know my specific cat's face when I type my fluffy cat, maybe textual inversion is enough, and it's tiny.
Could be, yeah.
If I wanted to generate anything landscapes, portraits, abstract stuff, but all in the unique artistic style of my cat. Like if my cat was a famous painter with a quirky line art style, then LoRA is probably the best bet, offering that balance.
That's a perfect way to put it, yes. LoRA excels at capturing those stylistic nuances, and DreamBooth might be if you wanted ultra-realistic pictures of your specific cat in various situations.
Got it. Now, you choose your method, you set up your training, but you said something earlier that really stuck with me about the data set being critical.
Ah, yes. This is so important, I really have to stress it. While choosing the right PEFT method and tuning hyperparameters matters, dataset curation is the single most critical factor for success, period.
More important than the algorithm settings.
In many, many cases, yes. No amount of fiddling with learning rates or training steps can magically fix a bad dataset. So many fine-tuning projects fail, not because the tech setup was wrong, but because the training images were inconsistent or noisy or didn't clearly represent the concept, or there just weren't enough diverse examples.
Garbage in, garbage out, basically.
Precisely. The model can only learn the patterns you show it. If the patterns are messy or contradictory, the results will be too. You might end up with a model that kind of captures your style but mixes it with weird artifacts or doesn't understand the concept reliably.
Okay, huge takeaway. Focus on the data. So what are the key steps to curating a good data set? How do you feed the model gold, not garbage?
It starts with sourcing and cleaning. You need to gather images that strongly and consistently represent the style or concept you want. If it's a style, every image should clearly embody that style. If it's an object, get clean shots from various angles if possible.
On cleaning.
Meticulously. Remove anything irrelevant, images that don't quite fit the style, pictures with distracting backgrounds, watermarks, other objects intruding. Be ruthless. Quality over quantity here to some extent, though diversity matters too.
Okay, clean, focused images. What next?
Pre-processing. This is about getting all your curated images into a standard format the model expects. That usually means resizing everything to a uniform square resolution, like 512 by 512 pixels, or maybe 102 by 104 by 1024 for newer models. Square. Always. Typically, yes, for most standard diffusion model training pipelines. And converting them to a consistent, high-quality image format, usually PNG is preferred, then just organize them simply, often just in a single directory.
Sounds like a bit of work.
It can be tedious, definitely, but it's vital. Luckily, there are great libraries to help automate the pre-processing part, like Hugging Face's own datasets library, or torchvision.transforms from PyTorch. They can handle the resizing, format conversion, etc. much more easily. But the selection and cleaning, that often requires manual effort and a good eye.
Right. Invest the time and the data up front. Okay, so let's say you've done that. You curated a great data set, you chose LoRA, you trained your custom model, and yes, it's generating amazing images in your cat's signature artistic style. Fantastic. Now, how do you make this usable? How do you get it running fast enough and efficiently enough for, say, a website or an app? This is the factory part, right?
Exactly. You've crafted your custom tool, and now you need to set up the production line. And optimization is absolutely non-negotiable here.
Why is that? My high-end GPU runs it okay.
Yeah, okay. On your local machine might mean several seconds per image, maybe even longer for high resolutions. For any kind of interactive application or a service handling multiple users, that kind of latency is usually a deal breaker. Users expect near instant results. Plus, running those big GPUs constantly is expensive. So optimization is about speed and cost efficiency.
Okay, fair point.
Yeah.
Seconds is too long.
Yeah.
So what are the essential steps to speed things up, to optimize?
There's a common stack of techniques people use. A very frequent first step is exporting to ONNX.
ONNX.
Open Neural Network Exchange. It's a standard format for machine learning models. You use tools, often Hugging Face's Optimum library is great for this, to convert your trained PyTorch model into this ONNX format. Think of it like creating a universal blueprint of your model's calculation.
I can move it.
Because then you can use specialized runtimes to execute that blueprint very efficiently. Which brings us to step 2. Accelerating with ONNX Runtime, or ORT. ORT is a high-performance inference engine developed by Microsoft. It takes that ONNX model graph and applies a whole bunch of clever optimizations. It might fuse multiple small operations into a single bigger one, optimize memory layout, things like that. It's specifically designed for fast execution, often giving significant speedups over running the original PyTorch code directly. And again, Optimum makes using ORT with your exported model pretty seamless.
So ONNX for the standard format, ORT for running it fast. What else?
The next big gun is quantization. This is about reducing the numerical precision used in the model.
Reducing precision, doesn't that hurt quality?
It can, potentially, but often you can reduce it quite a bit with minimal impact on the output quality, especially for inference. Models are usually trained using 32-bit floating point numbers, FP32. Quantization might convert the weights and activations to use 16-bit floats, FP16, or even 8-bit integers, INT8, or newer formats like FP8.
And why do that?
2 main reasons. Smaller memory footprint, an FP16 model takes roughly half the memory of FP32, INT8 takes even less. and faster computation. Modern GPUs have specialized hardware units like NVIDIA's tensor cores that can perform calculations much, much faster using these lower precisions. Libraries like Bits and Bytes make 8-bit or even 4-bit quantization relatively easy to apply, even during training sometimes. And tools like NVIDIA's TensorArt can leverage formats like FP8 for even more acceleration on compatible hardware.
So ONNX, ORT, quantization, do you use them together?
Absolutely. Often the best results come from combining them. You might export to ONNX, then use ONNX Runtime with quantization enabled, for instance. It's about layering these optimizations to squeeze out as much performance as possible.
Okay, the model is now lean and mean. How do you actually serve it? How do you wrap it up so users or other applications can call it?
Right, you need to build a service around it. A common approach starts with creating an API using FastAPI. Yeah, it's a modern high-performance Python web framework. It's really well suited for building APIs for machine learning models because it's fast and asynchronous. You'd typically create endpoints, like maybe generate that accepts a text prompt and returns an image, and maybe a health check endpoint.
And the model.
You load the optimized model into memory when the FastAPI application starts up. That way, it's ready and waiting to handle requests quickly, avoiding the slow load time for each request.
Okay, an API makes sense. What about deployment? Getting it onto servers?
That's where containerization with Docker comes in. Docker lets you package your entire application, the FastAPI code, all its Python dependencies like diffusers, ONNX runtime, etc., and the model itself, or at least instructions on how to fetch it into a standardized container image.
Like a self-contained box with everything needed.
Exactly. This container can then run consistently anywhere Docker is installed, whether it's your laptop, a colleague's machine, or a cloud server. It solves the works on my machine problem. A key best practice here, though, is usually not to bundle the huge multi-gigabyte model weights directly inside the Docker image itself, as that makes the image enormous and slow to transfer.
So what do you do with the weights?
You typically have the container download the weights from cloud storage, like S3 or Hugging Face Hub when it starts up, or you mount them as an external volume. Keeps the container image itself lean.
Got it. Container ready. Where does it run?
Cloud deployment is the final step, usually. You need servers with GPUs to run these models efficiently. You deploy your Docker container to a cloud platform that offers GPU instances. There's a spectrum of options here.
Like?
On one end, you have specialized platforms like Replicate, Banana, or others.
Yeah.
These often provide super simplified workflows, sometimes literally just connecting your Git repository, and they handle the scaling and infrastructure for you. Great for getting started quickly or for simpler use cases.
Easy button, basically.
Kind of, yeah, but maybe less control. On the other end, you have the major cloud providers, AWS SageMaker, Google Cloud Vertex AI, Azure Machine Learning. These are full-blown MLOps platforms. They offer much more granular control, integration with other cloud services, monitoring, automated workflows, everything you need for serious large-scale production.
But a deeper learning curve.
Definitely. There's more setup, more configuration, more concepts to learn. So it's a trade-off between ease of use and that fine-grained control and integration.
Right, so that whole factory stage is about speed, efficiency, packaging, and deployment. Always juggling performance versus cost and complexity.
You nailed it. It's all about delivering that creative power reliably and scalably. But, as you might guess, getting there isn't always smooth sailing.
The pitfalls. The path to production rarely runs straight, does it? What are some common nightmares people run into during fine-tuning or deployment, and how do you fix them?
Oh, there are plenty. Let's start with fine-tuning nightmares, a classic one. Your generated images are just noisy or blurry or full of weird artifacts, even after training.
What's usually going on there?
Often, it's underfitting. You just haven't trained the model for enough steps, or maybe you're not using enough steps during inference steps. The fix. Try increasing training epochs or steps, or during generation, bump up those inference steps. Sometimes trying a different, perhaps more robust scheduler can help too.
Okay, more training or more generation steps. What about the opposite problem? Images look too perfect, like copies of the training data, or there's very little variety.
Yep, that's overfitting. The model basically memorized your training set instead of learning the underlying concept or style. This happens frequently with small or not very diverse data sets, or if you just train for way too long.
How do you combat overfitting?
The best solution is usually a better data set. Larger, more diverse. Data augmentation techniques can also help artificially increase diversity. Or you can simply reduce the number of training steps. Sometimes regularization techniques might be needed too.
Right. Then there's the dreaded unstable training, loss values suddenly shooting up.
Yeah, exploding loss. 9 times out of 10, your learning rate is too high. The model's updates are too large, making it diverge. The solution is usually straightforward. Lower the learning rate, sometimes significantly. Using a learning rate scheduler that gradually decreases the rate can also stabilize things. Enabling gradient clipping, max grad norm 1 is a common setting, puts a hard limit on how large updates can be, which often helps prevent explosions.
Okay, lower learning rate, scheduler, clipping, got it. What about subtle failures? Like, the images look good, but the model doesn't seem to understand the prompt correctly anymore.
Ugh, loss of semantic understanding. This can happen if the model learns shortcuts or spurious correlations from your specific data set instead of the true meaning. Maybe it learns that your art style always includes trees, so it puts trees everywhere even when you don't ask for them.
How do you fix that?
That's trickier. You need rigorous evaluation. Maybe using tasks like phrase grounding. Can the model correctly place a red cube on a blue sphere? Sometimes freezing parts of the original model, like the text encoder, during fine-tuning can help preserve that crucial pre-trained language understanding.
So lots of troubleshoot just on the training side. Sounds like you need patience and systematic debugging.
Yeah.
What about when you try to actually deploy? What disasters await there?
Oh, yes. Deployment disasters are a whole other category. The number one headache is probably QT out-of-memory errors.
What about a GPU RAM?
Exactly. The model itself, or the batch size you're trying to process, or the intermediate calculations, activations, just exceed the available VRAM on your GPU. It's incredibly common.
Absolutely.
Several tactics. Reduce the train batch size, or inference batch size. Enable gradient accumulation steps during training. This lets you simulate a larger batch size by processing smaller chunks sequentially. Use memory-saving optimizations built into libraries like diffusers, such as attention slicing or flash attention. Apply more aggressive quantization, like 8-bit or even 4-bit. Or look into model offloading, where parts of the model are cleverly swapped between GPU and CPU memory, though that adds latency.
So squeeze the model into the available memory. What else goes wrong?
Dependency conflicts and version mismatches. This whole ecosystem moves so fast. Diffusers updates, PyTorch updates, CUDA updates, underlying library updates. It's easy for things to break.
Nightmare. How do you manage that?
Strict discipline. Use requirements.txt files with pinned known good versions of all your libraries. Don't just use the latest. Build your Docker containers from clean base images to avoid environment pollution. Always check compatibility notes between major libraries like Diffusers, PyTorch, and CUD versions.
Okay, lock down those versions. The last one,
Yeah.
you've deployed, but it's just slow, high latency.
Right. High inference latency even after deployment. This could mean your optimizations weren't sufficient, or there's a bottleneck somewhere else in your serving pipeline.
How do you diagnose that?
First, ensure you've applied the full optimization stack we discussed. ONNX export, ONNX runtime acceleration, quantization, then profile everything. Don't just time the UNet. Time the VAE decoding step, turning the latent representation back into pixels. Time any image pre-post processing. Time network overhead in your API. Find the actual bottleneck. Sometimes the UNet is fast, but the VAE decoding is slow, for example. For really demanding scenarios, you might need to look into more advanced serving architectures.
It definitely sounds like there's a lot to potentially trip over, but also a good set of strategies for getting back up. This field requires resilience.
Absolutely. Debugging and optimization are key skills.
So looking beyond the current hurdles, what's exciting on the horizon? What emerging trends should we keep an eye on in this space?
It's constantly evolving, which is part of the fun. One interesting area is advanced serving architectures. People are researching things like DiffServe, which proposes using cascades of models. Maybe route simple, easy prompts to a small, super fast model, and only send the really complex prompts that need high fidelity to a larger, slower, more expensive model. It's about optimizing the cost-performance trade-off dynamically.
Smart. Tailor the tool to the job in real time.
Exactly. Another trend is towards end-to-end simplification. While we've talked about multi-stage optimization, some research is showing really good results with simpler, more direct fine-tuning and deployment pipelines. The community is always searching for ways to make this powerful tech easier to use effectively.
Streamlining the process.
Right. And finally, just the expanded scope of diffusers itself is worth noting. It started primarily with images, but the team is actively expanding it to handle video generation, audio generation, maybe even other modalities, all while trying to maintain that core modular philosophy we discussed.
So the skills learned with diffusers for images might transfer.
Very likely, yes. Mastering this library and its concepts feels like a good investment in understanding future generative AI capabilities across the board.
Wow, what an incredible journey we've covered today. We really dove deep, didn't we?
We certainly did.
We went from the really elegant core idea of diffusion models reversing noise, inspired by thermodynamics, all the way through the practical tools like the diffusers library.
Highlighting that crucial modularity.
Exactly. And how that enables fine-tuning, especially the balanced power of LoRA that's become so popular. Then we tackled the factory floor, optimization with ONNX and quantization, and the deployment pipeline using fast API, Docker, and the cloud.
Covering those common pitfalls, too.
Right, the nightmares and disasters.
Uh,
But also, crucially, how to troubleshoot them. And we landed on that critical point about data curation, maybe the single most important piece for successful fine-tuning. And always that trade-off in production between speed, cost, and quality.
it's a constant balancing act.
So, thinking about all this, as generative AI like diffusion models gets even better, faster, more efficient, and the tools like diffusers make it more accessible and branch into new areas like video and audio. Here's something to think about. What new creative frontiers does this open up for you? If you can fine-tune a model on your specific style or generate niche content easily, how might these tools change the very definition of creativity or content creation for you as an individual artist, designer, developer, or just someone with an idea? What will you build with it?